Welcome all to this new session which discusses the kinetics of a particle, but this time we will describe the motion using the normal and tangential coordinates. So the main objectives is to establish the kinetic relation in normal, tangential, and binormal coordinate system. We are going to talk about this B later. But basically what we are doing is exactly like what we did in chapter 12. We started with studying the kinematics in rectangular coordinate, then we study it in the normal tangential, and then we will go to the cylindrical as well. So the motivation here is to study the motion of objects like racing car or satellite as they move over curved linear path, and we will see that it is convenient to utilize the normal tangential coordinate than, for example, the rectangular coordinate in those kind of problems. So to define the normal tangential coordinate, we assume that this particle P is moving in a curved linear path as shown, and that coordinate system is going to be attached to the particle. Now, what we understood from our experience in chapter 12 is that the tangential axis is always tangent to the path. So it is not difficult actually to construct this axis. You just need to know the point, determine the tangent, and this is going to be the direction of the tangential axis. We also, if you remember, discussed that the direction of the positive is supposed to be pointing toward the direction of the motion, where the motion is. So this particle is moving in this direction, and this is why the tangent is considered to be positive in this direction. If the particle is moving in this direction, then the tangent has to be on the other side. Now, the other axis, which is the normal axis, is perpendicular to the tangent, and it has to point toward the center of the curvature right there. Now, the only new term here, which is a new axis that we haven't talked about before, is the normal axis, which is named as the binormal direction. And this is basically a result of the cross multiplication between these two vectors, which is a vector perpendicular to their plane. Now, having said that, if we want to write down the Newton's second law, then we will have the summation of all forces equals to the mass, which is a scalar, multiplied by the acceleration vector. And since we have three components of forces, then we can say that we should sum up all the scalar forces acting in the tangential direction, and we should multiply this by the tangential unit vector plus the summation of all normal forces as a scalar multiplied by the unit vector in the normal direction plus the summation of all of the forces acting on the binormal over there multiplied by a unit vector, we will call it UB, which is supposed to be equal to the mass multiplied by the acceleration in the tangential direction plus the mass multiplied by the acceleration in the normal direction. It is important here to note that the motion is considered to be happening over this plane, the plane where the normal and the tangential axes are. So if the motion is happening along this plane or is going in this plane, then the particle is never going to move along the binormal direction. And for that, it will have no acceleration. And this is why we have only tangential and normal components of the acceleration. So if we want to write the previous equations in three different directions, then we can say that the sum of all of the tangential forces is equal to the mass multiplied by the tangential acceleration and the sum of the normal direction, forces in the normal direction, is equals to MAN, and the sum of the binormal forces is equals to 0. Now we should also remember that AT is equal to dV over dt, which is basically V dot, while AN is equal to V square over rho, where rho is the radius of curvature. Now, of course, if we write down these three equations in this format, we should also specify some sort of a positive direction. So maybe this one is going to this direction, maybe this one is going to this direction, and this one is going to this direction as the positive. We should recall that whenever the path of the motion is defined by an equation y equals to fx, then as a reminder, the radius of curvature rho is equal to 1 plus dy over dx square, all raised to the power 3 over 2 by d2y over dx squared with the absolute value. Now let's see how we can draw the free body diagram for an object being analyzed using the normal tangential coordinate system. So here we assume that the object is this one and it is moving downward. So if it is moving downward, then as we agreed, then this is the direction where the tangential axis is supposed to be positive. Now we don't need to do a lot of work. All what we have to do now is to have a right angle in order to establish the normal direction, which is right there. It's perpendicular to the tangential direction. Of course, both the tangential acceleration is going to go on the tangential axis and the normal acceleration is going to go along the normal axis. Now, since the motion is moving in this direction downward, then apparently the friction force would also have to be tangential because it is always tangent to the surface. But this time, it's going to be on the opposite direction. It always opposes the motion. Now, also, we will see that the normal force is supposed to be perpendicular to the tangent over here, which is going to be in line with the normal axis. So this is Fn. So the only force here which is not acting along either the normal or the tangential direction is the weight, which is mg, because weight is always acting in the direction of the gravity. So this is just a continuation of what I discussed in the previous slide regarding the normal force and the friction force, where we said that the normal force will act along the normal direction, while the friction force is going to act opposite to the direction of the motion along the tangential axis. So as a reminder again, it will probably be necessary to utilize the kinematic relations AT, the tangential acceleration, equals to dV over dt, which I already stated before, but this is just another reminder, and AN, which is the normal acceleration, which equals to V squared over rho. Now let's work on this problem, which says that the design of the skier jump, shown over here in the figure, requires knowing the type of forces that will be exerted on the skier, right here, and his approximate trajectory. In this case, the jump can be approximated by the parabola, which is given by this equation. And what we want to determine the normal force on a 150-pound skier at the instant he arrives at the end of the jump, which is point A, right here. where his velocity is approximately measured as 65 feet per second. Also, what is his acceleration at this point? So quickly, to draw the free body diagram, we would have to do it right at point A. So at this point, where the tangent is horizontal, we will have the normal force acting in this direction, and this is the normal direction. As you see, this is n. We assume that the acceleration, the normal acceleration, is going to point toward the normal, toward the center of curvature, is supposed to be right somewhere here. The weight of the skier is 150, and this time the weight is collinear with the normal direction, because the normal direction happens to be along the y-axis or the vertical. Also, the tangential coordinate is right here, and as the skier is moving toward this direction, then we would know that the tangential positive has to point toward the direction of the motion. So this is where the tangential acceleration is positive. So let's start writing down the equations of motion. We start with the tangential direction, taking left hand side as positive. So the sum of the forces along the tangent equals MAT, which gonna give us 0 equals to 150 divided by 32.2, which is multiplied by 80, which is going to give you 80 equals to 0. You're probably asking, why 0? Because there are no forces, even friction. This is skiing over snow, has almost no coefficient of friction, and this is why there are no forces, and this is 0. 150 was divided by 32.2 because this is the weight, and you have to divide it by the gravitational acceleration in feet per second square in order to get the mass. So regardless of this, you are going to get 80 equals to 0. So let's move on to the next direction. The next direction, we take it upward as positive. The sum of Fn equals to Man, which is going to give you Na minus W equals to 150 divided by 32.2 multiplied by velocity squared divided by rho. Now, this is the normal acceleration. We have been given the equation of the curvature, which was a parabola. Y equal to 1 over 200 x squared minus 200. But what I want you to remember is that I'm just going to approximate the curve, which was parabola. It was going this way, and the thing that maybe I didn't emphasize on when I was talking about the diagram in the previous slide is that we establish a coordinate system such that this direction over here is the positive y, and this direction is the positive x. So what you are actually getting here is this at this point where x is equals to 0 and y is equals to 0. This is very important when we write down the curvature equation. So the curvature rho is equal to 1 plus dy over dx squared, all raised to the power 3 over 2 divided by d2y over dx squared. We don't forget the absolute value, but also we remember that this is at location where x equals to 0, right there. So what are we going to get? We are going to get 1 plus x divided by 100, and this one is squared, all raised to the power 3 over 2 divided by 1 over 100, and this is of course at x equals to 0. So what are we going to get? We're going to get rho equals to 100 feet. From the previous calculation, we can calculate Na, which is equal to 150, the weight, plus the 150 over 32 0.2 multiplied by the velocity 65 squared divided by 100, which is the radius of curvature. This is going to give you 347 pounds. Now, just to remind you that this one is the velocity, this one is the radius of curvature, this one is the mass, which is equal to the weight over g, and this one was the weight of the skier. Now, to find the acceleration in the normal direction, it is equal to v squared over rho, which is equal to 65 squared divided by 100, which is equal to 42.25 feet per second square. Remember that AT is equals to 0. So this is the only acceleration component, which is greater than 0. Let's now work on this interesting problem where we have a ball that has a mass of 30 kilograms and a speed of 4 meters per second at the instant when theta is equals to 0, right there. We want to determine the tension in the cord when theta equals to 0 and the angle theta at which the ball stops momentarily. Now we know that the ball will swing going this way up, it will stop, and then it will swing back. It will stop momentarily at this position, so we want to know what is this angle. Here we establish both the kinetics and the free body diagrams at the location when the ball is at this position. So what we have at this position, the weight is acting downward, the tension is acting upward, and since this is the basically center of the curvature right here, then this is the normal direction, and since the motion is moving toward this direction, this is going to be the tangential axis. Now for the kinetic, we know that what we will end up with as a resultant of this unbalanced forces, we are going to get two kinds of acceleration, m by at and m by an, which are acting both in the tangential and the normal direction. So in order to find the tension in the cord at the location when the angle theta is equals to 0, we need to start by writing down the equation of the motion at the normal direction. So the summation of Fn equals to man. Now what do we have here? We have tension as positive because it is acting upward, minus mg negative because it's acting downward, is equal to mv squared over rho. Now, so this will give you the tension equals to m multiplied by v squared over rho plus g. And if you substitute, the mass was given as 30 kilograms and the velocity was given as 4, so this is square. And if you remember, at this position and even at this position, doesn't matter, the cord, the length of the cord is always 4 meters. So we will have here, this one is divided by 4 plus 9.81, and this is going to give you a tension of 414.3 Newton. The next step is to find the angle theta over there at which this ball is going to stop momentarily. So we take this position and we analyze it. So at this position, if you look at the free body diagram, we have the normal direction acting toward the center of curvature right here. So this is the normal. And as this is the tangent, we construct the tangential axis over here. And since the motion is moving upward, we take this one as positive. Of course, we have mg acting downward, so we have to decompose it into two components. The result, which is the kinetic diagram, is mass by two acceleration components. So let's start with the tangential direction. So this is the positive direction, and this is the sum of Ft, which is equal to MAT. The only force that we have acting along the tangent is mg sine theta, which is indeed negative, not positive. It's pointing toward the negative side. So this is going to be minus mg sine theta is equal to MAT. Clearly, we can cancel out the masses over here, and what we will get is AT, which is equal to minus 9.81 sine theta. Now remember that the theta is unknown. Now we can make use of some of the relation that we derived in chapter 12. One of them, which we said that it's going to be useful, is this relation. A ds equals to v dv. Also, we can have another relation established from the arc length, and which is s, theta, and r. So if we write down this equation as ds is equal to the radius, which is 4 multiplied by the change in the angle, d theta. Now if we combine these two equations and setting the acceleration as the tangential acceleration, then we will get 4 at d theta equals to v dv. So from the previous slide, we got at equals to minus 9.81 sine theta and 4 at d theta equals to v dv. So now I'm gonna set up the integral. So I will integrate from 0 to theta for minus 4 multiplied by 9.81 by sine theta d theta, which is going to be equals to the integral from 4 meter per second to 0 for v dv. Now I can see that this part, this is constant, so if I want to rewrite the integral, I will get minus 4 multiplied by 9.81, the integral from 0 to theta, sine theta d theta, which is equal to the integral from 4 to 0 v dv. If I integrate, I will get minus 39.24, and this is minus cosine theta from theta equals to 0 to theta, which is equal to 1 over 2 v squared from 4 to 0. So I get negative sign over here and negative sign. So if I multiply them, I get positive. So I end up with 39.24 and cosine theta minus 1, which is equal to minus half 4 squared. Now, if you look carefully over here, when I substituted cosine theta, I get theta. When I have cosine 0, I get 1, and I have to subtract. Here, I substituted cosine v as 0, so I got 0 minus half by v squared, which is 4 squared. Now, if I work out this, I will get cosine inverse of minus 8 divided by 39.24, that's a 4, plus 1, and this is going to be 37.2 degrees. So this is basically the angle at which the ball will stop momentarily. So to summarize, we have established the kinetic relations using normal, tangential, binormal system. We also shown that the direction of the friction force is acting along the tangent in the opposite direction of the motion, the normal force is acting along the normal direction, and the weight is always acting vertically. And that's it. Thanks a lot.